Look at this single, straight pathway. In basic linear programming, execution travels strictly line by line along a fixed route. It processes commands exactly as written, from top to bottom, without deviation. But real-world data is unpredictable, and to handle it, that rigid track must be able to fracture into a complex multi-directional network of branching routes. To build an intelligent system, a script cannot simply run blind. It has to break this linearity, evaluate the data it receives in real time, and react to changing conditions. In programming, we call this dynamic routing decision-making. It is the ability of a system to check specific conditions and deliberately redirect execution to entirely different blocks of code based on the results. Every decision point acts as a logical fork in the road. No matter how complex the evaluation seems, it ultimately resolves to a simple binary state. The condition is either true or it is false. Python relies on a specific set of syntactical tools to construct these intersections. Keywords like if, elif, and match case serve as the physical switches on the track, controlling the flow of logic. Mastering these conditional structures allows you to take a static, rigid list of instructions and transform it into a reactive state machine, a program fully capable of complex algorithmic routing. The foundational logic gate in Python is the if statement. It functions as a strict, localized barrier. It presents a condition and requires that condition to evaluate exactly to true before execution can pass through to the code inside. Python defines the physical boundaries of these execution blocks using strict syntactical markers. The first is the mandatory colon, placed at the end of the condition, which acts as the structural opening of the gate. The second marker is mandatory indentation. Any code pressed against the left margin sits outside the gate. By indenting the lines immediately following the colon, you visually and functionally bundle them into the execution block guarded by the if statement. This logic model maps exactly how that gate operates. On the left, we set our threshold, if age is greater than or equal to 18. When the input value of 18 drops into the node, the condition evaluates to true. The gate opens, and the logic flows cleanly downward into the execution block. But watch what happens if the input fails to meet the criteria. If we change the age to 16, the node evaluates to false. The gate locks, and the logic flow actively bypasses the execution block entirely, continuing down the main script. To capture that diverted flow, we introduce the else statement. This serves as the default alternate route. When the primary if condition fails, the execution is automatically caught by the else block, ensuring a defined action is still taken. This setup creates a mutually exclusive routing system. We see this mechanics precisely in the formula to find even or odd numbers. By dividing an integer by 2 and checking if the remainder is 0, the logic perfectly splits. Even numbers travel down the if path, and all remaining values travel down the else path. The if-else construct operates as a complete binary state machine. It guarantees that between two potential outcomes, one and only one path is chosen. Binary choices handle direct intersections efficiently, but systems routinely encounter multi-state routing. An application rarely operates on just two mutually exclusive outcomes. It needs to categorize data across a wider spectrum of possibilities. Python handles this architectural challenge with elif, short for else if. This keyword allows developers to chain multiple, distinct conditions together sequentially. This diagram illustrates a grade system built as a vertical logic pipeline. Successive thresholds are established at 90, 75, 50, and 35. Let's send a value of 60 marks down the ladder to observe the evaluation sequence. The variable hits the top rung first. 60 is not greater than or equal to 90, so the beat registers as false, rejecting the value and dropping it to the next level. It encounters the second threshold. 60 is not greater than or equal to 75, another false evaluation, and the variable falls again. Finally, it hits the third rung. 60 is greater than or equal to 50. The condition registers as true. The state changes, the gate opens, and the execution flows directly into the grade C block. Notice the mechanical rule that triggers upon success. Once a true condition is found, the system immediately bypasses all remaining lower conditions. The ladder terminates, routing the flow entirely out of the pipeline. elif ladders prioritize chronological hierarchy. The script does not exhaustively test every possible option. It evaluates from top to bottom, executing the very first true statement it encounters and ignoring the rest. Sequential ladders evaluate one condition at a time. But certain logic routes depend on overlapping prerequisites, demanding multi-dimensional constraint checks before granting access to a block of code. A developer achieves this by building a nested if statement, an architectural decision tree where an outer gateway serves as the primary guard and an inner gateway serves as the secondary. This hierarchical flowchart maps out a job eligibility script. To reach the final execution block, the input must pass through two sequential locks. First, the outer gate verifies the applicant is at least 21 years old. Only when that pathway illuminates green does the logic proceed to the inner gate, which independently checks if the applicant holds a valid degree. Deeply nested statements successfully map out these constraints, but physically indenting code deeper and deeper into the margin creates excessive syntactical depth. This can quickly make a script difficult to read and maintain. Python allows developers to flatten these physical nests into single compound evaluations. By utilizing logical connectors like AND as well as OR, multiple distinct criteria can be tested mathematically on a single line. The standard leap year algorithm serves as a rigorous stress test for this kind of compound Boolean math. Look at the logic equation for calculating a leap year. It processes 3 parameters simultaneously. First, it isolates the inner rules, checking that the year is perfectly divisible by 4, but using the AND connector to verify it is not divisible by 100. Then it expands, applying the OR operator to automatically include any year divisible by 400, collapsing the entire sequence into a single true or false node. Mastering this Boolean arithmetic enables a developer to compress complex, multi-layered decision trees into highly efficient single-line logic tastes. Relational evaluations dominated Python logic for years, but Python 3.10 introduced an entirely different architecture for routing data. This is MatchCase, a structural pattern matching tool that brings functionalities similar to SwitchCase from other programming languages natively into Python. This diagram compares a multi-operator calculator side by side to highlight the structural difference. On the left, a traditional elif ladder tests the operator string mathematically, line by line. On the right, the MatchCase architecture analyzes the variable up directly against a predefined set of physical cases. Instead of evaluating mathematical truth over and over, MatchCase maps the input variable directly to its corresponding slot. The multiplication token snaps instantly into the asterisk case, completely bypassing the chronological checking required on the left. If an unrecognized symbol drops into the system, Python catches it using the underscore syntax. The case underscore block operates as a catch-all fallback, fulfilling the exact same role as a final else statement. This specific architecture is highly optimized for discrete values. If a script needs to parse exact menu selections or specific string inputs, pattern matching handles it with precise efficiency. While if and elif rely on calculating mathematical thresholds, MatchCase operates on structural identity. It provides a cleaner, more explicit architecture for explicit routing. Control flow structures grant a program immense capability, but they demand absolute mechanical precision. Python relies entirely on flawless formatting. A developer's intent means absolutely nothing if the syntactical structure is broken. Look at this condition, if 10 is greater than 5. It mathematically makes sense, but omitting the mandatory colon blinds the interpreter. Without that marker, Python cannot see the start of the block, triggering an immediate syntax error. Even with the colon fixed, spacing dictates hierarchy. If the next line misaligns and shifts to the left edge, the parent-child link between the condition and the execution is physically broken, throwing an indentation error. But the most dangerous failures are logical mistakes, creating silent bugs. Dropping the equal sign from a passing grade threshold alters the math entirely. The code runs without errors, but the logic gate now blocks the exact data it was supposed to let through. Strict syntactical hygiene ensures the logic remains mathematically sound. It is the absolute prerequisite for designing functional, predictable algorithmic state routes. We can see the culmination of all these distinct control flow architectures when we bring them together into a complete real-world application, such as an ATM simulation. This map illustrates how core logic evaluates a user's choice. From a central input node, the program is perfectly routed by a central if, elif, else cluster, dynamically pulling the execution sequence into separate, isolated states for checking a balance, depositing funds, or withdrawing cash. Within these individual states, the standard if statement establishes solitary, localized conditions, triggering specific security checks or isolated actions. The else-else block serves as the strict binary fork, cleanly splitting logic to handle scenarios like sufficient versus insufficient funds. And the elif ladders and match case structures sit at the top level, scaling the overall logic up to handle these complex, multi-state environments smoothly. Mastering these structural gates bridges the gap between static instructions and interactive software. It allows developers to elevate simple text scripts into intelligent systems capable of reacting dynamically to the unpredictability of the real world.